Hi, welcome everyone. Today's presentation is going to be the first part. It's going to take us more than one session to get through this. But recently at the KDD conference, there was a tutorial, as you see on your screen here, called Inference Optimization for Foundation Models on AI Accelerators. This is really about how do you do inference? How do you serve up LLMs? Which is really a different problem from optimizing the compute for training LLMs, for example. So there are some different techniques, and there's just a lot of work that has gone into it, especially as these models have gotten bigger and bigger, and they don't easily fit, say, for example, on a single GPU, something like that. So you can see the AWS team, who knows a thing or two about um, cloud and scale and serving. They're the ones that led this presentation. So the materials that we're using are their slides, and they built this wonderful outline. And so the cool thing is we can just follow along and really look at all of the different technologies that are important for inferencing. So today there's some foundations, just a primer on, like attention and everything, and then we'll take a look at the architecture of LLMs, transformers, and some of the architectural choices, and then eventually get into some of the other cool techniques that are used on the server side to be able to serve lots of people and speed up inferencing. So this is intended to be a discussion, generally always is, but especially more so today in the sense that this is not my presentation. Um, I I volunteered to lead the discussion, but these these are not my slides, and so in some places I will explicitly call out and say, "Hey, this is something that, if anybody else wants to share about, if they know more about this, please chime in." And as per usual, at any time, you can raise your hand. Feel free to ask a question. I'm not on my usual computer setup. It may be a little bit harder for me to monitor the chat than usual. So feel free to use the chat. I will do my best. But if for some reason I'm not getting to you, if you have a question on the chat, try the raise hand feature, and I think that might be a little bit easier. All right. So with those preliminaries, we see here where there's an even bigger team at AWS that was behind the info in this presentation. So huge props to them. Thank you so much for putting this together. And so what we're going to start with is just something that probably doesn't need a lot of explanation, that there's been the rise in large language models, but corresponding with that is also this rise in cost. So you see two different charts here, and both of them are showing just how much larger these models have been getting over time. As things go to the right, the models, get bigger and the cost goes up. And this affects certainly training. Early on, that was a big discussion. People were like, wow, they spent $100 million to train this model. But now that, ChatGPT came out, and millions and millions of people using LLMs, you pretty much can't shake a stick and not see LLMs in the news. One of the problems is, wow, actually just doing inference on these very large models gets very expensive, and it also can be very slow. So that's really what we're going to dive into over the next likely 3-4 sessions. Really just depends on how many questions people have, how deep the discussions we get into. There will be many topics here, just to be upfront. There'll be many topics where we could devote an entire session just on one topic. And so there may be things that we decide to follow up later, some things we go into more detail, some things less. So here is some data that helps sort of show as we get increasing adoption, what is the shift in cost between training and inference. At one time, nobody was using LLMs really, and 100% of the pie was training, and it was training being done by academics and big labs like, the OpenAIs and whatnot. So now you see like training is this small 15% of the pie, and the whole rest of the pie is all the compute um, from people actually using LLMs. So this has become the bigger problem.
Hey, Ted,
Yeah, Roger.
have you heard anything about what is I'm kind of surprised to see the edge inference as large as it is. I assume that's just for LLMs, right?
Yeah, yeah, I'm assuming that this is, well, it says here AI silicon, so maybe it's not. So that would explain it,
Okay,
right?
okay.
Um, but the same concept holds. They say, hey, uh, GPT-4 may have taken God only knows what to train, but they really only trained it one time. And maybe there's some fine tuning they do where they release updates, approximately monthly or whatever. But, OpenAI has like whatever, million unique visitors a day, crazy number. Um, so as much as they spent on it, there is a lot of compute going to serving these models. All right, so here's an outline of the entire tutorial. Uh, we're not going to get through everything today, obviously. But you see here just talks about LLM inference, and then a little bit about um, the architecture for hardware accelerators, an overview of what are the different opportunities for speeding things up, and we'll probably get through like architecture choices and stop there. And that might look like it's about halfway, but really the material gets a little denser. And so that's why I think it'll be like 3, 4 sessions for us to finish going through the rest of the material. Oh, and then they also have these case studies at the end. I don't think we'll do those. Maybe that can be kind of a follow-up conversation. All right, so LLM inference, um, let's just take a look at this. So I'm going to assume everybody here has heard of the transformer. Hopefully you're fairly familiar with the architecture. We'll go a little bit into this diagram from the original Vaswani Attention is All You Need paper. So in this paper, we've got these two components. On the left in the blue is the encoder, and on the right in the red is the decoder. And so people today talk about LLMs based on whether or not they have one or both of these components. So encoder only models, things you've heard of like BERT and all of its variants. So Roberta, Daberta, these models, they only use the encoder half. And one of the key things about the way these models are trained and used is that all tokens attend to all other tokens. And so you can, if you're a word early in a sentence, you can actually attend to words that come later in the sentence. So the typical use for these types of models has to do more with things like meaning, because it's more powerful if you can look both ways than if you don't look one way. And so your typical sentence encoders use this type of architecture. The decoder owner model is what's shown in the red, and in fact, because this middle part here that's blacked out is where the encoder information gets fed in, you don't need that because you have no encoder. And so almost all of the LLMs that are in the news are decoder only. So GPT-2, 3, 4, Llama, Mistral, Claude, you name it. Famously, importantly, the way these models are set up, tokens can only attend to other words that came earlier in the sentence. And so these models are used auto-aggressively so that you predict the next token, right? And they cannot see the future, because if they could, then they would just cheat. They would already be able to look at it. And then there is encoder decoder models. The original Vaswani paper was used for translation. So you could like put English into the encoder, you could get French out of the decoder. The most well-known model that actually used this architecture, the way we think of LLMs, is the T5 model. Very, very rare that anybody actually uses the full encoder decoder model. So in this talk, as with almost every LLM, famous LLM that we're talking about, is decoder only. So then this conversation is purely going to be focused on that. There's probably some slightly different things you need to do if you want to serve up BERT to 1 million users, but the reality is people are not serving up BERT to 1 million users, and lots of people are serving up, you name it, your Gemini, Bing, Chat GPT type models to millions of users. Okay, so quick review here of the attention mechanism. So within the transformer where the attention is happening, basically this is a mechanism where you compare. By the way, I often say words and tokens interchangeably, even though I know it's not scientifically correct, just because it's a little more intuitive. It flows a little bit better off the tongue. So any place where I say word or token, I really only ever mean token, but sometimes I just say it to be a little bit more colloquial. So this means that at any token position where you're calculating something. So in this case, we're talking about autoaggressive LLMs. So we're predicting the next token. So the very last input token is the one that is then going to predict what is the next token. And it has the benefit of being able to see everything that has come before. And so this attention calculation, everyone always talks about, it's like, oh, well, basically what you can do is you can do this calculation with the queries and the keys, and you can decide, how much you want to pay attention to previous words. And in case it's like not obvious, like people usually don't actually say, what are you trying to calculate? What are you trying to pay attention to? So I thought I would just momentarily touch on the fact that we don't really know exactly the mechanisms, what happens. It's a little bit of black magic. So that's one of the reasons why people don't say, is we don't know exactly what's happening. But if you have a sentence like I'm having trouble thinking of a good sentence, but so the husband wanted to give something to, and it's going to be his wife, right? It's going to be his in the English language because the pronoun is referring to husband. And so in that circumstance, you would want to look back, whatever, 5 words, and be able to do this. What exactly, again, is happening in here? There's a lot of very complex calculations. There's probably, we assume there's relationships between adjectives and the nouns they modify. There's relationships between subjects and verbs, possibly between subjects and objects, verbs and objects, all these kinds of things. So we really don't know exactly what is happening, but we do know that language is complex, sentences are complex, and you need a way to be able to refer back to things that were said earlier in order to have a complete sentence, a complete paragraph, a complete chapter, a complete whatever. And so thus the attention mechanism, and I won't go it again. We could spend an entire session just talking about attention or contrasting it with RNNs or whatever. All right, 1 second here. Okay, yeah, good. So somebody posted the slides. So yes, the slides that I'm going through, I may occasionally flip to a different document, but this set of slides I have not altered. This is the original AWS slides. All right. So how do you actually calculate this attention? We need to talk a little bit about this just because we're going to get into, right, how do we speed up the calculations? So we better be clear on exactly what the calculations are. So for this step one, at any given layer, you have your input. At the very first layer, the input is the token itself. At higher layers of the transformer, it's been modified. It's no longer just the original input. And so for this input, it's going to go through essentially a fully connected layer, MLP, a dense layer, whatever you want to call it. That's the equivalent just basically of a matrix multiply. And it's going to the input is going to get converted to a new value, which in this case we'll do one conversion that we will call the query, one conversion we will call the key, and another we'll call the value. So these are linear projections. It's a rectangular weight matrix, and historically, by convention, these are always square weight matrices. So if you say that your input tokens are vectors of length 4,000, then the queries will also be length 4,000. The keys will be length 4,000. The values 4,000, with a caveat that we get to later. This technically does not need to be the case. However, I'm not aware of anyone who's ever actually tried doing it any differently. So you see here, this diagram on the right, the way you can look at this is the top position is the first token. This is the second token, and we're saying this is current, and this whole thing will repeat up to whatever arm. In this diagram, they have capital T as like sort of the maximum length. So you can imagine the sentence is, my name is blah, blah, blah. So the second word is name. And so name is going to come in, and you're going to get a query, a key, and a value from that. So that's step one. Step two is we're going to calculate attention scores. And the way that works is for any given query, you're going to compare it to all of the keys. So for the very last one here, with the one that's positioned capital T, you're going to dot it with every key that came before it. All, in this case, T of them. Sometimes you see L, sometimes you see N. Since they are pulling from different documents here, the terminology and the naming is not going to be identical on every diagram because they're coming from different blogs, different papers. Okay. Sorry. But so the important thing though is that you have to calculate the dot product between this query and every other key. So if you look here in this diagram, you'll see it's Q2 over and over and over again, but you have all these other different keys. And then you run these dot products, which are dot products can be a scalar number. You run them through softmax, and you'll have a bunch of attention values that sum to 1. Okay. And obviously the bigger ones, these are the higher attention scores. These are the words we're going to pay more attention to. And the ones close to 0 are not going to contribute to this particular calculation. And then the final step is once we have these attention scores, these sum to 1, what we're going to do is we're going to multiply this weighting to get a weighted mix of the values that we calculated in the very first step. And so if you had attention scores that were 1 for one of them and all zeros, then you'd just be purely pulling out one of the values. But if Typically, you're not going to have anything quite that extreme. So you could have a 0.6 here and a 0.2 there and a 0.1 somewhere else and a bunch of 0.05s and so on and so forth. All right, maybe I'm going too slow, but just want to kind of make sure we're all on the same page. And then this is the critical attention calculation that that people have difficulty with trying to figure out how to speed up. It's not necessarily actually the majority of the flops in an LLM, but the other parts are simpler. And so if they're just matrix multiplies, everyone knows this is exactly what you got to do. There's really no other shortcut for speeding up a giant matrix multiply. All right, so then I said there's one caveat. So people are familiar, there's multi-headed self-attention. And so then the idea is that if you have a very, very large model dimension, again, typically the letter D, so let's say it's 32,000. A 32,000 length vector is very, very expressive. It's got a lot of components to it. And doing one attention calculation really means you're only allowed to do, like I was saying, one calculation of what you want to pay attention to. But so what you could do is you could break it up into chunks, and you could say, I will do 16 different calculations. And this means that in parallel, maybe adjectives and nouns can have an attention score for what they're doing to calculate something. And nouns and verbs can do something else, and so on and so forth. And in practice, all the LLMs do this. There's not too much discussion about this because through clever math, not going to go into it here, but basically, if you take a 32,000 and divide it up into 16 chunks of 2,000, then you just concatenate all those 2,000 so that it looks like it's something that's like 32,000. The calculation of the queries can be done in one fell swoop, and the keys and the values. They can be done in one fell swoop as if you were not doing multi-headed attention, as if you were just doing one single headed. Where things get different is when you're actually calculating the softmax, you now have to do that per, group of 2,000. But otherwise, all the matrix multiply and other stuff kind of works the same. The one thing that is different when you're doing multi-headed attention is because you're only going to calculate your softmax score across this smaller section, it does mean that later on we'll talk about you can actually partition the different heads onto different servers. And you could have, for example, 16 different servers, each doing one head's calculation in parallel, and everything would be fine because there would be very little, basically almost no communication necessary between the different servers that are calculating the attention for the different heads. All right, and then we have another slide here that kind of puts it all together that says, okay, you've got this on the left, you've got this this LLM. It drives me crazy. Sometimes you see input at the top, sometimes you see input at the bottom. In this case, the input's at the top and the output's at the bottom. But nevertheless, you've got multiple layers. Typically, you're going to have like 24, 32, numbers like that. So one single layer gets blown up here on the right. And if you were to kind of make like a gate circuit diagram of what's going on, it looks like this. So typically normalization happens. Well, in this case, we're talking about Llama itself. So this is exactly how it works. So normalization happens at the beginning. You do these matrix multiplies to calculate your queries, keys, and vectors. The queries and the keys, they get multiplied together. That's the dot product. The softmax gets calculated. This gives you your attention scores on that sum to 1, and you multiply those by the values that you've calculated over here. Once you've gotten those, there is an output projection matrix, which often people don't talk about. People forget to sort of talk about that. It's very important for understanding how the the LLMs can actually work in terms of like what information they're writing internally, but it's not really terribly important for understanding the concepts of attention and whatnot. But so what you see here is there's four of these weights where you're doing regular matrix multiply, and you have these two multiply signs where you're doing additional large matrix to matrix multiplication. And then Llama does not have a standard MLP second half. This gating looks a little bit different. A standard one would just have two weight matrices, and the first one would blow up the dimensionality by a factor of 4 typically, and then reduce it bound by a factor of 4. So it's just a 2-layer fully connected dense MLP. This is a slightly different architecture. If you're familiar, like with Mamba, you'll see this shape as opposed to just sort of the standard 2-weight design that's in the original Vaswani transformer. So when we do this, you can see here's some of the numbers for Llama 2 7 billion. It has 32 transformer layers. The hidden dimension is 4,000, so that's the length of our tokens. They're 44,000 floating point numbers. This intermediate size is inside the MLP, where it projects it up by a factor of 3, so it goes to 12K. The attention is split 32 ways, has 32 heads, and the total vocabulary, which is not terribly important for today's discussion, but there's 32,000 words that in the original vocabulary that get embedded into our 4K size model dimension. All right, so now we're going to get into some of the interesting part. This is the part where we're going to talk about what happens when you actually do inference. So let me just pause here. We've covered the preliminaries again, assuming most people are have heard of transformers. So any comments or questions before we proceed? Okay. So typically when you or I use an LLM, we have a prompt. We have some type of question that we're putting into the LLM. And so maybe, for example, I want to ask it to reword the description on my resume. So I say, hey, you are a expert in human resources and helping people find jobs. Below in quotes is the first paragraph, the introduction to myself and my resume. Please reword this paragraph so that it will impress hiring managers. And then you have quote, a big long paragraph, and then the end of that paragraph, and then maybe you repeat the instructions a little bit and you say, please rewrite this paragraph. And then it's going to go and spit out a paragraph, right? So conceptually, what we can do is we can process one token at a time, just the way an RNN would. But the reality is, for the first, 200 tokens, that's all part of what I wrote. We don't care what the next token prediction is. We already know that the next token is going to be the one that I wrote. So the prediction is really completely irrelevant. So if I wrote 200 tokens and it ended with, please rewrite this paragraph, then what we really care about is starting with the next token, the actual predictions. However, in order to calculate the 201st token, I do need to do all of the attention calculations, the queries and keys and all of that on the first 200 tokens. Let me flip to a diagram here real briefly. You see these type diagrams in some places, and so I just wanted to kind of show this briefly. So queries and keys, they come from the same information. They're going through different weight matrices, and if you're trying to like visualize what's going to happen in terms of like which ones are going to get multiplied, which ones are going to get masked out, often you'll see this sort of triangular diagram like this. Okay. And so in this case, I've put the queries on the y-axis in rows and the keys here in columns. And so the oldest query, the query for the very first, the 0th token, it's only able to see itself. It's only able to see key 0. And then the last one can see them all. But so for this last one, query n, where I'm about to predict token n plus 1, when we do that calculation, we're going to need all the keys and values from all of the earlier tokens in order to do that calculation. So let's continue with the slides here. And it's going to talk about the prefill stage, and you're going to see this little miniature of what I just showed before. So this is just miniaturizing. It's only length 3, but imagine the first 3 tokens of your sentence are, I think this, and it's trying to predict the 4th token. You don't need, at this point, when you're predicting what word comes after this, you don't need the query information for I or think or this. But you do need the keys and values for I, think, or this. And once you've calculated them once, they're never going to change. So the keys and values for think, once you calculate them, you can use them for predicting the 4th token. You can use them for predicting the 5th, 6th, 7th. They're never going to change once you've calculated them once. So conceptually, even though you could do these 1 token at a time, I, and then think, and then this, it's much faster if you just do large batches and you plop all of them into your transformer at once. So what you do is for all the tokens that are in the prompt, you want to pass them in one giant chunk conceptually, one giant chunk, and calculate all of the keys and values at every layer for all the positions that are in your prompt. So I've been saying 200. So if my prompt is 200 tokens long, I'm going to have 200 keys, 200 values at every one of my layers. And for the 201st token prediction, I can use all of those and do a calculation 1 token at a time then for what the next token is. So you can see here, it says in the bullets, right? We're going to do forward pass on X being our full length 200 tokens. It's not a single token, our 200 token wide input, and calculate all the layers of everything. And you don't really hear about this when you read a paper, okay? The papers just talk about what calculations you're doing. But the key thing is we're going to save this off. We're literally going to reserve memory, and we're going to put copies of all of these keys and values. Let me just check the chat real quick. How do you translate a token to a query and a key? So this is part of the transformer architecture. When the token comes into a layer, there's a weight matrix that is trained during training, and you multiply the token by that weight matrix, and it outputs a vector, which is your query, or it outputs a vector, which is your key. Again, we don't really know exactly what's happening under the hood, but that's the operation. And so the output from one layer becomes the input for calculating the queries, keys, and values of the next layer. So you have to do all of these calculations sequentially, layer by layer, in order to calculate all the queries, keys, and values, and in particular, the keys and values. The queries will not be reused by later token positions, but the keys and values will be needed for later token positions, and the keys for, as I was saying, for token position 2 will be the same no matter what token we're predicting. Whether we're predicting the 3rd token or the 3000th token, the keys and values for token position 2 are always the exact same floating point numbers. So I hope that answered the question. All right, so when we do this, the key bullet here is that we're going to have some larger matrices. So in the case of, it said that the model dimension was 4,000. So if I have 200 tokens, each length 4,000, that means I have a 200 by 4,000 array. That's my input token data. Then it's going to calculate queries, keys, do this attention, do the MLP part, and it's going to have a new 200 by 4,000 array. That's the output of layer 1, which is the input to layer 2. Those are nice, moderately beefy sized matrices that can keep a GPU or some other accelerator busy for a while. And so it's much more efficient to pass all 200 of those in at once than it would be to just pass them in one at a time. Yeah, so the transformer architecture, the very first thing that happens, so essentially the goal of the transformer is to calculate attention scores and use those as weights for the output values. In theory, you could take your inputs and you could directly do something to calculate the scores, but that would not be very expressive in terms of how powerful it could be. By having a layer of indirection in between, where you have a matrix multiply, what that allows you to do, for example, is to say, very super simple one would be, is if you had a few ones and all zeros in the rest of that matrix, what you would be is you'd just be pulling out a subset of your original input. You say, I only care about this part, these where we have the ones, and I'm going to use that. And so hypothetically, if your long 4,000 vector has information in it about whatever, different concepts, maleness, femaleness, color, size, whatever, do I have a noun or an adjective or a verb that I'm holding in my concept? Then what you can do is you can use this matrix to pick out the part that you really are interested. So maybe at some point you care on the query if you're an adjective, and for the key you carry if you're a noun, you care if you're a noun. And so then the adjective, you want to know the combination of this token position is an adjective and that token position is a noun. And so that's why you have to have these weight matrices that give you much more expressive power, because you can choose which particular things you want to actually dot together to get the highest score. So that means that when you have multiple attention heads and you have multiple layers, they can do all sorts of complex calculations because they get to choose what parts they're actually going to pay attention to. So I hope that helps. So this is the process of choosing what you think, how do I say, without getting too, what you think is important for you to pay attention to. That's what you put in the weight matrices, is what am I going to say is important. You're going to actually calculate what to pay attention to, and then you're going to weight the values based on what you decided to pay attention to. And so in this pre-fill stage, which is similar to when we're training LLMs, we're going to put in a whole bunch of tokens at once because it's much more efficient to do that computation. After step 1 is done, we're going to get to step 2, the decoding stage. The decoding stage is autoregressive, and we can only do 1 token at a time. So we do not have that that efficiency of use of computational resources. So if you see this little mini diagram on the right, okay, you say, okay, I now have 4 tokens. I think this is, and I want to predict what's the 5th token. I only have 1 query. Before we had multiple of them, now I only have 1. I'm not going to necessarily make as efficient use of my computational resources. So you can see the first bullet, it says, hey, we're going to generate these tokens sequentially, one at a time. The cool thing is I have keys and values for I think this is, and if the next word is, let's say, A, I think this is a great, blah, blah, whatever. Once we input, I think this is A, all the keys for I and think and this and is are the same as they were before. And all the values too. So the cool thing is we get to reuse these keys and values. One of the bad news things, though, is it's actually going to take a lot of memory to store all these keys and values. So we can trade off repeating a whole lot of expensive computation just by caching these keys and values, but that is a non-trivial task when you say that each key and value is 4,000 floating point numbers, which natively are 32 bits, so are 4 bytes each. So 16,000 bytes. And I've got 32 layers in here. And oftentimes we're now talking about, long contexts. And so when you get into 8,000, 16,000, 30,000, you're now talking about 30,000 times this 16,000 bytes for the key, another 16,000 for the value, times 32 layers. What you see here is you're quickly getting into the high billions of numbers. And so these KV caches implemented just naively, right? Uh, uh, they're gonna need to be huge. They're actually, as much as we say, wow, these models are big, 70 billion parameters or whatever, the KV cache is actually going to be even bigger than that. So that is going to be a problem for inference. That's something that, again, when we're just reading all these papers about training these models, that doesn't come up. But it turns out that the KV cache is actually more of a memory hog than the model itself. All right. Not gonna spend the time to go through this exact calculation. But we saw this diagram for llama, and here is the cost for doing the prefix part, the prefill for the prompt that was given at the very beginning. So the prompt is length capital L, and our model dimension is lowercase d. So in this case, this is the 4,000 we've been talking about. So you see some quadratic terms here. Okay, so you have 12 times the length times whatever d is squared. And we also have length squared times d. So as the model gets bigger and d gets bigger, this first term gets really big. So if instead of 4,000, it's 32,000, it's 8 times bigger. This term becomes 64 times bigger. If you want to support super long contexts, which people really want this, they want, to be able to put, like, paste in, entire PDFs and things like that, and have the LLM do lookup and question answering based on these documents, then this is the term that then blows up, where you have your L squared D. So supporting a context length of 100,000 instead of 4,000, that's 25 times longer. That's going to have this term be 600 times bigger. Okay. And then you've got some constants on here, but you see 12LD squared plus L squared D. Once you get into the inference to output one token, the math they're showing here is 12D squared plus LD. Okay, so there is an L factor in here. It's not quadratic. However, this is only per one token. So anytime you want the LLM to be able to output a lot. So if you only want it to be able to have a really long context, but how much it's going to say is never more than 1,000, whatever, then you don't really have to worry about this L term that much. But if ever you were going to say, well, my max sequence length is, 100,000, and the LLM might get a short prompt and actually output 100,000 tokens, now you're talking about 100,000 times this term right here, the LD. All right. So these are the naive costs, and this is the problem that we're going to run. We haven't talked about memory yet, but this is one of the big problems we have in terms of how do we serve this up and then serve this up for like millions of people. All right. Any other questions at this point? Okay, so moving on here. There's a slide here that says, hey, let's talk about the importance of this KV cache. And so again, I think we covered this. If you didn't have this KV cache and you output, I said, hey, please rewrite this paragraph, and it rewrote the paragraph, and it was 1,000 tokens. It would be doing all of these transformer calculations on everything over and over again 1,000 times. And instead, it's only having to do each one once. It's just storing them. So like say it's instead of quadratic, it's a linear number of calculations, just 1,000. However, here's some data they say. So for Llama 2 7 billion, which is the really small Llama 2, right? I think it's the smallest. I don't think they've released one that's smaller than 7 billion. For the very, very smallest one. So this is not 70 billion. This is not the new 3.1405 billion. If you have 2,000 words in your prompt, it's a gig of memory. If you have 8,000 words tokens in your prompt, it's 8 gigs of memory. And since these are servers that normally are serving multiple users, if you had 4 users with 8K sequences, that's now 32 gigs of memory you need just for the KV cache. And it's now bigger than the actual Llama 2 7 billion model stored with lower resolution 16-bit weights. So this can be a really, really heavy problem. I haven't looked, but they have a Medium article here that they linked for this diagram for explaining KV caching. Any questions about KV caching? We're going to get into next session complex KV caching schemes, but any question about just like the basic KV caching, the fact that for token position 2, the keys and values never change, so you can reuse them over and over again for future queries. Okay. And then I think here it just goes into a little bit more about what the calculation is. So it's 2 because there's a key and there's a value, hidden dimension size times the number of layers. This is kind of what I was saying. And then precision bytes. So if it's 16 bits, it's 2 bytes. If it's 32 bits, it's 4 bytes. On your GPU, obviously you need other things. It has intermediate tensors it's calculating. It has some CUDA reserved memory and blah, 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 blah. And so again, just some different math showing how much memory. So I think of as a consumer, an RTX 4090 is a pretty high-end GPU. And it says that if you've got Llama 2 7 billion loaded on it and 1 big of cache memory, then basically you can handle at most 1,000 tokens, even on the smallest Llama 2. Again, we're going to get into other tricks and whatnot, but this is just naively loading the model with 16-bit weights and whatnot. All right, check here. How do we prevent single point failures for KVs? I'm not quite sure what you mean by single point failures. So maybe you can clarify that. I don't know if there's anything that can handle a hardware failure, if that's what you're talking about. Yeah. Yeah. So basically my understanding is there's like error correcting memory that you can put in servers. So you can use some kind of like ECC memory or whatever. But basically, if you have an error, you're just toast. I don't think there's really any support for what to do if that happens.
One thing you might add there is that the KV cache is just a cache. So you could, if you still had the token sequence, you could still regenerate the cache.
Oh yeah. That's a fair point. You could regenerate them if you had a problem, but I don't think there's any sort of like try catch, kind of logic going on here. They're optimized for super fast inference, and they're just assuming nothing's ever going to go wrong. So, um, and there's probably other layers in terms of like APIs where something might be able to get, like resubmitted. Not necessarily like what you're saying, Roger, like very cleverly resume right where you were. They probably could just like start the whole thing over again. Yeah. No, you guys are really smart. So like, yes, you absolutely could rebuild the KV cache. I've never heard of, I don't, I'm not an expert on hardware and serving, but I don't think people, think about those things. If you're serving 1 million users a day and this is something that maybe happens once, you probably just resubmit the user's request from scratch in a very unclever way. And instead of rebuilding the cache, you just like say, oh, that's weird. That one errored out. I'll just rerun the whole thing from scratch. It's probably far simpler than trying to find the code to figure that out.
I think this line of questioning is kind of interesting, though, Ted. Sorry to interrupt. Just I've been thinking about it in the context of like, let's say, legal discovery, where you have to have a bunch of documents. You could almost think of the KV cache, I think, as like an embedding memory or a memory of embedded data. And so if you needed that to persist over the course of, instead of a couple queries, like months or years or whatever, I would imagine you could just serialize it and then reload it, though, no?
Oh yeah, like I don't know how it works, but like with ChatGPT, I can click on old questions that I asked and then I can resume those conversations. So to all of your guys' points, it would be really clever if when they did that, they just persisted to disk what the KV cache was at the end of that conversation. And so then when I say, yeah, yesterday I had this long, complex legal conversation, I fed you all these large documents, blah, blah, blah. I have a follow-up question. That would be brilliant. I don't know if that's actually what happens.
The only thing is that the multiple between the sequence, the token sequence size, and the KV cache, in this example, it was 1,000. I think as the models get larger, it gets even higher. So it may still be worthwhile just if you're, rather than save it to disk, is just say regenerate it when you need it.
Yeah, it really depends. But the questions are good. The point is valid. This is gold, right? And so whether it's an error or whether it's you're expecting a user to come back or whatever, uh, in fact, even when I have an interactive session and I ask blah 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 blah, and then I ask a follow-up question, to the computer, if it took me 2 minutes to send that follow-up question, that's an eternity. So they probably did just like save. They could have done it either way. They could have either saved the KV cache, or if that's too expensive, they could have just recalculated that first part, over. It's an interesting trade-off, but you guys are exactly right in terms of like how it works. Is that if you want to, you can keep it around, you can persist it, and if you didn't persist it, you're okay, you can always recalculate it. You're dead on. Okay, so we're going to go a little bit further today and then pause, wrap things up here. So here's a little bit of a background on how hardware accelerators work. This is a very, very light primer, okay? If you guys are interested in deeper, hopefully somebody else here can go deeper. So just very super lightly, you see some pictures here, right? You see Cerebras, you see Grok. What do they put on those chips? What kind of hardware is in there? That's the high level question we're going to ask. So there's going to be some different elements. If you look down here in the lower right corner, okay, here are the things that they have in common. They're going to have matrix multiply hardware. Today, it's absolutely necessary to have support for lower precision numerics, not just floating point 32, IEEE 32 or 64. You need as fast bandwidth memory as you can have. And then they say large per device, fast-ish memory. And then if you're doing really big stuff, you need really good interconnection bandwidth, because what we're going to see is these things get so big, nothing fits on one chip. Nothing fits on one GPU. Nothing fits on one anything. And so you're going to end up having a bunch of interconnection communication costs. And so the higher that bandwidth is, the less of a penalty you pay for doing those. So just a couple more slides here, a little bit more detail. So one of the bullets was rich data types. So typically you're going to expect at a minimum, here's your vanilla IEEE float 32, really great, but it's very expensive. And so other things that people have supported are these tensor floats, brain floats, float 6, IEEE float 16, these float 8s that I'm not so familiar with. And nowadays you see not only integer 8-bit, but now really pushing for 4-bit integer multiplication. And if you think about the cost of these different data types, they have a chart here that shows you roughly. So ease of use on the right means that basically you can use these data types and you don't have to worry about overflows or underflows. You can just kind of use them without having to think about it. And there's no sort of conversion or quantization, chunking, whatever. So it's a little bit harder and harder as you go to the left. But then in terms of speed, I don't know if this is a super accurate y-axis, but you can see that as you get smaller, the 16 bits are a lot faster. And then the 8 bits are even faster. So this is where basically, as far as I'm concerned, at some point, we get all this for free because some people did some research, some people did some hard work, and then everything got coded into your GPU and got coded into PyTorch, and we just get to say, hey, do this thing, and it's like magic. So, there's a lot of hard work behind the scenes, but to us, using something like 8-bit integers or brain float 16 can be completely, sometimes as little as like 3 lines of code, and it's just completely behind the scenes. Sorry. So here's a slide showing one of the most expensive, most important operations your accelerator needs to do is general matrix multiplication. So the left is showing dense matrix multiply, the stuff that you were taught in school, college, where you do one row of one matrix times one column of another matrix, and then you're going to accumulate those because, right, you have multiple rows and columns that are summing into the same cells. So that's where you see this sort of multiply, add, accumulate architecture at the hardware level. There are also support for sparse matrices. And so if you have a bunch of elements that are zeros that aren't contributing towards your calculation, you can have some sort of much fancier architecture that's choosing some subset of elements to actually multiply and accumulate. I don't really know how these sparse architectures work. It's obviously depends on the degree of sparsity, and it's pretty cool stuff that they get some of this sparse stuff to go quite a bit faster than the dense multiplication. And there's a couple slides here on the Amazon stuff. So they have their new Neuron Core V2. And what they have is they have the matrix multiply stuff, this tensor engine. They also have 1D vector multiplication. And I believe that this thing can be specialized to do things like softmaxes. Scalars like a CPU, and then they have this general purpose SIMD thing that I guess you can kind of like write your own sort of core instructions, as it were, and have them run on blocks of memory if you're trying to create some operation that they haven't really support. So then another slide here, you see what their slightly modified architecture for either the Trainium or the Inferentia chips. But you're going to see all of these on there. So the chip has matrix multiply, which is the main thing that we need for transformers, maybe a little of the vector as well. But they support lots of different workloads, not just LLMs. So that's the general thing, and then there's a hierarchy of memory on all of these devices, where typically you have your SRAM that's super duper fast, very close to all of this compute, but it's going to be small. We're talking like megabytes, not gigabytes. And so that'll be one of the patterns, is how can you maximize use of that super fast memory as opposed to the high bandwidth memory, which is fast, but still not as fast as SRAM. So a very simple thing you can do high level is you can take your work. And so if you imagine this is our LLM, and we have layer 1, layer 2, layer 3, layer 4. We can do tensor parallelism. We can do we can divide the data between different servers. So here, worker 1, worker 2, worker 3 is going to represent different servers, different hardware. And so especially if this green data for layer 1 doesn't even fit on 1, you almost have no choice but to split it this way. Okay. You'll notice that these horizontal dotted lines that represent the separation between the workers, every time one of these, whatever blue, purple lines crosses that dotted line, that means that you need that fast inter-device communication. Okay. So it would be preferable on the right to do pipeline parallelism, where you say like, oh, let's let worker 1 calculate the first 2 layers, then pass it off to worker 2. And then worker 1 will start doing the first 2 layers for the next batch, for the next job, right? There's going to be fewer lines crossing these dotted lines in general. In this simplified diagram, it may not look like it, but there'll be fewer data crossing these dotted lines. That's ideal. But again, so they support both of these models. But the reality is, if these LLMs get big enough where one layer doesn't even fit on one device, you have no choice but to do some type of tensor parallelism. Okay, so let's see here. We can go a little further. Any questions before? Just do a little bit more before we pause here. Yeah, let me just check. Yeah, so we are recording. The person who usually posts the recordings is traveling town extensively, so I don't know if they will get posted as timely. But West Coast Machine Learning on YouTube, and somebody else maybe can help me out and post a link into the chat. And then when you, if somebody could also repost the link to the slides. These are not my slides. I'm currently going through the Amazon team slides as is. All right. So the next thing we can say is when we're looking at doing inference, here we're talking about users actually using these LLMs. It turns out that there's multiple things that we might want to talk about. So let's actually define our metrics. So the first thing that's going to happen is you wrote your prompt. We're not going to process it one at a time. We're going to do it efficiently in a big chunk. And then when you get to the end of it, it's going to predict the very first new token. And then we're going to iterate going one token at a time, token, 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 token. So this first metric that is of interest to a lot of people is time to first token. So TTFT is how long does it take you to do just this main part, okay? And so you can imagine for something like a chatbot that's interactive, this is super critical. And so we're going to want to use our tricks that we talk about over the next couple sessions to shorten this. If you pay attention, you'll see that some of the APIs, people are providing discounts for sort of batch mode stuff, which means that they do not need to worry about fast TTFT. Okay, you're saying, hey, I'm going to submit 100,000 things, and I just want you to serve it up in an hour, in a few hours, whatever. And so I'm not sitting here waiting for it. 1 second. Okay, and then the second thing that's super important to people is then how fast do you spit out the remaining tokens after the first one? And it turns out, interestingly enough, that because humans can only read so fast, that if you're doing a chatbot, you don't actually need ITL, intertoken latency, to be as fast as possible. Now, obviously, if you're slow and you're 5 seconds between tokens, then yes, you want that to be faster. But once you get to a certain point and they say like 6 words per second, getting it from 6 words per second to 10 words per second may not actually really buy you much with your users. And so if instead of getting that from 6 to 10, you could do something else, like reduce TTFT or do whatever, that's probably a viable trade-off. All right. Thanks, guys, for reposting that stuff. Okay. And so obviously they say here the things that affect it is how big your model is, how long your people's inputs are, what the hardware is. And then ultimately for inter-token throughput, it does depend on your batch size. So if you're supporting multiple users, then that is going to obviously use more of the hardware resources than if you're just serving one person at a time. One person at a time would not be terribly efficient, however. All right. So then if we look at the whole thing, there's actually some things that need to happen prior to the prefill we talked about in the previous slide. And there's some things that need to happen at the end. So you could talk about this end-to-end latency. And so this is like if you were generating an image, the user might not really care so much about, time to first token. They might not care. They're like, hey, just how long did the whole thing take? And yeah, that includes all your API and all the other pre-processing and post-processing and stuff. So there's your NT. Another thing that you can look at is your your maximum request rate, or famously, if you're using people's APIs, what a lot of people run into is queries per second, QPS. So QPS is important to users who have a lot of data that they want processed. QPS is also important to you as the guy doing the inference, because that's basically saying, for the X many dollars I spent to buy a server, how many queries per second is it going to actually, respond to in order to serve my users? So there is very clever load balancing that you need in order to get this all perfectly. But basically, what we're going to get into is what are the techniques that can improve these different metrics. Sometimes there will be a trade-off between one metric or the other. In a perfect world, you have a technique that only speeds things up and doesn't actually have a trade-off somewhere else. All right. So what are the things that we can do here? You see this little diagram, this little tree on the right. Our model architecture within system optimization, management, efficient computation, batching, scheduling. So we'll talk a little bit about some hardware stuff. And then in sessions like 2, 3, I don't know if we need a fourth session, we'll talk about some of the stuff that's like quantization, distillation, but some of the things that I think are really cool that at least maybe it's just because of my selectivity of like what papers I read, but I just hadn't seen as much of this cool stuff with how clever people are managing the KV cache and managing multiple users and scheduling people and things like that. Really, really cool. So question about hallucination. So not going to talk too much about hallucination in this talk. Basically, all models give bad answers. If you have a model that predicts housing cost, sometimes it's going to do really, really good, and sometimes it's going to just do a terrible job and maybe mispredict the cost of a house by a lot. To a certain extent, I think of LLM hallucinations as being the same thing. A lot of times it's going to give you really good answers, and every now and then it's going to give you a real clunker. And there's a lot of research going into that. People are trying to reduce it, but there's no real real specific cause for it. And to a certain extent, well, if we knew what the cause was, we would have fixed it by now. If I knew that the car had a flat tire, I would have changed the tire. So, but it is something that I think it's important to understand that all models, even the simplest ones, even linear regression, make bad predictions. It feels different when it feels like an LLM is talking to you and it says something. But the reality is all models do make bad predictions. It's not exactly the same, but so so question about applications. I'm not really sure. So LLMs, started with just text. Now we're figuring out ways to tokenize other information. So use for images or whatever. But the reality is, if you look, you'll probably see LLMs being used for just about everything. So whether it's biology, chemistry, finance, you name it. Sorry if I didn't quite answer that question. Feel free to re-ask if I missed something there. Okay, so I think we'll be able to just start on, maybe we won't finish. But in terms of just a little bit, couple slides here in terms of fast inference. So when you're talking about a 70 billion parameter model, we've got some serious compute and memory issues here. Okay, so half precision 16-bit floating point numbers, Llama 2 70 billion. You need 140 gigabytes of memory just to load the model weights and not do anything else. No computation, no KV cache, no nothing. Obviously there's specialty hardware out there, but I don't think NVIDIA makes a single GPU that can handle 140 gig. This is that computation we talked about during prefill. It has an L squared D and an LD squared component to it. And then the KV cache, the longer the context, right? Gemini says they can support 1,000,000 length inference. So that KV cache, we're talking 1,000,000 times blah, 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 blah. However many floats, however many layers. That's just a crazy, crazy amount of memory. So there's two high-level things that we can talk about. First here, can we reduce the computations we need for keys, values, and queries? And can we reduce the computations we need for that MLP part, the projection part? Okay, and so there's two answers that people have. One answer is group query attention, and the second is mixture of experts. These are fundamental architecture choices of your LLM model. This is not something that you, as someone standing up a server, can just choose that this is what you want to use. Okay. So this has to be designed in. The stuff we talk about later will be choices that you can just make on the serving side. So briefly, group query attention says, hey, in a regular, the way we've described it, in the prefill stage, you have to calculate for each query its connection to every other key. So for query 0, we dot it with every key. Query 1, we dot it with every key. Query n, we dot it with every key. At the extreme on the far right, you could say, I'm just going to have one key and one value, and I'm going to reuse those for all queries. And people found that they can really speed this thing up, but it just doesn't work that well. The attention calculation, unsurprisingly, the attention calculation just gets to be quite poor. So the middle ground is you say, okay, fine, I won't go from n keys all the way down to 1, but I am going to cut it down. I'm going to cut it in half, or I'm going to cut it in by a factor 4, and we're going to share these. And that turns out that doesn't necessarily cause too much of a performance hit. So this is a pretty good middle ground that people are building into the architecture of LLMs. And so then you can see here that this is, if shown here, it reduced by a factor of 2, then this cuts down the size of your KV cache by a factor of 2. So it's less computation, and it's also cutting your memory in half. So it's a double win in terms of using the grouped query. The other thing you can do on the MLP side, you can do mixture of experts. So if people have looked at Mixtral, then basically what you're doing is you're having multiple of these feed forward layers, and for any one given token, you're only going to use a fixed amount of them, either 1 or 2 usually. And so the amount of compute is the same as something much smaller, but in terms of the performance of the model, because it's using different ones of these feed forwards for different tokens, it actually is more powerful than if you just had 1 or 2. The other benefit is that if you had, let's say, 16 experts using only 2 at a time, you can spread these experts out over 16 different servers. And at any one point in time, this particular user only wants expert 1 and expert 7. But it's going to average out that all of the, or people design it so that all of the experts are used equally, so that the workload on all the experts averages out. And so that's a great way to, again, use parallelism to speed things up.
Hey, Ted.
Yes.
Yeah, quick question back on the group attention.
Yeah.
Do you know, is it basically a reduced number of keys and values, or is it more of a superpositioning of keys and values?
It's a good question. I haven't looked that much into it. I would assume that if you're sharing a key and value between a pair of tokens, that you let them both contribute. So you're doing some kind of superposition of the two.
Okay.
That you wouldn't just like, I'll calculate it on the first one and just throw away the second one, right?
Right.
So that's my guess. But it's
Thanks.
a great question. Maybe we'll see if we can get a definitive answer before next week when we resume. Okay. So then again, mixture of experts, that's way. So again, these are architectural choices people make because they know that these models will need to be served. They doesn't necessarily, these changes to the architecture do not help necessarily with how long it takes to train your LLM. Okay. These are choices that people made because they know ultimately we're going to need to serve these models. And I believe that's the last slide. Yeah. And so here, again, wonderful list of references that they have in this presentation. And so these are the references for this section. So this is where we decided we were going to stop for today. And so next week, we get into things like flash attention, if you're familiar with that, and then some gnarly KV cache stuff that I was unaware of, chunk prefill and stuff like that. Some really cool ways that they try to schedule all the work so that it keeps your hardware, your matrix multiply units, as busy as possible. All right. Any final questions before we wrap up for today?